Okay, Monday, 16th of October, laws of motion. We're still here at laws of motion. And then we're gonna have uniform circular motion. Okay, that's how. And last thing that we did was we're doing lab 2, and at the beginning of lab 2, we covered forces. Okay. So at this point in time, you should worry about those forces here, okay? For now, you should worry about those 3 forces: normal tension and force of friction. Those 3. And the other ones are gonna come later. Trust we don't have those 2. We're not gonna deal much, but you have to know that they exist. Okay, fluid drag, yes, we might do one problem on that. For those ones, you have just this one, this force here. And the book also have, I didn't put here, there's another force, the weight can also be written in a more generic fashion. Okay, I'm gonna give you the formula later on. Okay, so but for now, concentrate on those 2, and later on you're gonna cover this one here, the force of friction as well. Okay, where did I stop here? Okay, so we finally formulated Newton's first law of motion completely. Okay, if the net force applied on object 0, the object will be either at rest or moving its constant velocity. The converse of the above is also true. Okay, if an object is at rest or moving its constant velocity, then the net force applied to this object is 0. Memorize that for the rest of your lives. Okay, so more students coming in. Page break. And 1823. That's the one, Newton's first law of motion. And there are a bunch of problems that we're going to use Newton's first law of motion. And start getting used to this law. Okay, let me give you a few more examples. Not just the law, but also the free body diagram. Free body diagram is very important. Here you go, that's the free body diagram, right? Free body diagram shows all the forces applied to the object. And grid line, I don't like the grid line. The grid line make the picture look so ugly. So, but sometimes we need the grid line to line up the objects there. Good. Okay, so here you go. Free body diagram. What's that? Okay, that's the tension. Let's see here. Yeah. So you have a string here. In this case, you have a string attached to the object. Okay, the string has no tension of whatsoever. But as I apply a force to the string string is going to become taut like that, and there will be a tension applied to the object. If the object doesn't move, If the object doesn't move, what does it mean? It means that we have something called the force of friction. And there are two types of force of friction: the static force of friction and the kinetic force of friction. Okay, here you go. If the object is moving, right, and the object is moving is constant velocity, in this case, the object is at rest. If the object is moving with constant velocity, it means that the force of friction that we have is going to be the kinetic force of friction. There is a very important difference between those two forces. Okay, I'm going to comment in more detail about that, and let's see if I have more. Oh yeah, I have more. Here we go. Example of free body diagram, right? We did that, but now we're going to do in more detail. We have this object at rest. Its subject is always subject to the weight. If it's resting over a surface, it's going to have a normal force applied to it. And the net force of this object is going to be zero because it's at rest. If the object is moving, if the tension is to the left, it means that if the object is moving, it's constant velocity. You know, V equal to constant. I'm gonna put like that, magnitude, even better, instead of magnitude of V. The speed, right? I mean the speed here. It's better this way. Constant greater than zero. Net force is going to be zero. Examples, right, of Newton's first law. We go. This one, where you covered that. I can have attention applied to an object. Here's another one. Attention applied to an object. The object is not moving. The object is not moving because we have a force of static friction, but you can have a second force applied along the horizontal. And the object is still at rest. Net force is still equal to zero. Okay, here you go, another one, another example, very interesting example. There are all sorts of examples, okay, that you can keep in mind. I'm trying to cover as many as I can so you can become familiar with it, right? So let's go back one by one. Here we go. Example of free body diagram. I'm gonna document here for you. The simplest of all free body diagrams that you're going to see that uses Newton's first law of motion is this one that you see here. Examples that use Newton's first law of motion. Okay, simplest one is an object at rest over a surface. Okay, we have the following force. We have the following forces: weight and normal force. Simplest, okay. Accordingly, the equation is going to be given by, here you go, one is an object of mass m. I'm going to put it of mass m, okay, at rest over a surface. We have the following forces: weight and the normal force. Accordingly, the Newton's first law is going to be written as, and I'm gonna get this one here, copy and paste. Okay, go. net force. Oh, I forgot to put the vector symbol, right? Net force is equal to weight plus normal. Okay? Because the object is at rest, we have this relationship here. Strictly speaking, we can write down the weight as mean mg, and let's not forget that the direction of that force is going to be along the y-axis, but it's going to be along the negative y-axis. And I had the drawing further down, right in here. Here you go. That's the drawing that I have. The weight is downwards, the normal is upwards. No forces along the x-axis, right? So if I come to you and ask you, what is going to be the value of the normal? In this case, the normal is going to coincide with the weight. The only difference is that it's going to be upwards because it has to cancel the weight. Okay? Example 1. I'm going to put here example 1. Now we have this other one here. And it's a little bit more complicated. Let's get a simpler one before we go into that one, right? Yeah, this one here. Yeah, let's take a look at this one here. And I'm going to put it here, v equal to 0 as well. V equal to 0. If v equal to 0, it means that we must have a frictional force acting here on this object, like that. Okay, and in this case here, it's going to be the force of a static friction. Oh, not this one. Not this one. This one here. Yeah, this one right here. Okay. Example 2, right? Let's take a look. Example 2. An object resting over a horizontal surface. There's a tension. Apply this object with V equal to 0, resting. An object at rest over an horizontal surface. There is a tension applied to this object. Since there is a tension, okay, there must be to the right. Since the object at rest, since the object is at rest, comma, there must be another force acting against this tension. This force is the force of friction, okay? Friction, specifically the force of static friction, F sub S. force of static friction. Consequently, it's force of static friction because the object at rest, right, is called the static friction because the object is at rest. Consequently, the equation for the net force is, okay, so here you go. I'm gonna use the same relation. Here you go. W plus normal. We have the tension. I'm gonna call it T. And then we are going to have the force of static friction. Okay, that's gonna be like that. Objects at rest, so the right side of the equation must be 0. Well, what you see right here, what you see above, above is in reality 2 equations. One along the y-axis, and the one along the y-axis is this one here. I mentioned that, I sort of mentioned that before, right? Is this one right here. And the other one along the x-axis. And the other one along the x-axis. Like that. Okay, when we solve that for the normal, for instance, there was an object, and I gotta put of mass m, right? When we solve that for the normal, for instance, since we know the mass, you know the weight, right? And then we solve for the normal, we get something like that. And let's say we know what the tension is. So if we end up finding, if we have to find the force of static friction, we get something like that. Okay. In terms of the components, we can write that equation like what? Minus mg y hat. Right? I'll leave the n like that. If I know the tension, right? If I know the tension, I will write like that, you know, tension, magnitude of the tension along the x direction plus force of static friction, which is also along the x direction. It's going to be like that. Okay. Here I'm doing examples only for v equal to 0. And I can have something more complicated. Okay. Suppose that the tension makes an angle theta with the horizontal. That's a problem slightly more complicated than the other one before. Okay. So another example. Example 3. Example 3, an object of mass m at rest over an horizontal surface. There is a tension applied to this object to the right, making an angle theta with the horizontal. Since the object is at rest, there must be another force acting against this tension. It's for the force of friction. Specifically, the force of static friction. It's called the force of static friction because the object is at rest. Consequently, the equation for the net force is going to be, it's still gonna be like that. But then it's gonna be, but now my tension is going to have a component along the x direction. and another component along the y direction. If we look back here, you can see that both tensions, both components of the tension are along the positive direction. And I'm going to get this one here. Here you go. So there is no doubt that those components let's see, I'm gonna put here, I'm gonna put here, I'm gonna put here. This one is I'm gonna put here as well. Okay. So there is no, oh, there is a little change here because now my normal will be affected by this component of the tension. Okay? So we must have a third term along the y-axis that's going to be given by that. And when we solve for that, for the normal, when you solve for the normal, let's see here, we're going to have this relation. Yeah, let's not forget, right? There is one more thing and one more step. We have to take one more step here. Why is that? We have to take one more step because this weight, as you see here, has that mg, right? What's that? Y hat. But let's not forget that this mg has a negative sign here. Okay? And this negative cancel out with this negative. One negative cancel out with the negative. And we get this relationship here. Notice that this new normal is going to be less than the other normal that we calculate for the other problem. Okay? The magnitude of this new normal is going to be less than the magnitude of the normal of example 2. Okay, that's because we have that y component of the tension in the problem. Along the x-axis, we are going to have this other x component here of the tension. Okay. Which is going to affect my force of static friction. Want to be like that? Okay. Let me give you another example that's going to be important as well. There you go. If the tension were to be downwards, then the normal force would be more the other one, right? So let's go for another example with the tension downwards instead of upwards. If you had the tension like that, right? Another example. Example 4. An object of mass m at rest over an horizontal surface. There is a tension applied to this object to the right, making an angle theta with the horizontal, make an angle theta downwards with respect to the horizontal, Okay, so here this other one is making an angle theta upwards, huh? With respect to the horizontal. So go ahead, make sure you do the free body diagram. And this one here, I wanna, let's see, I want to copy this one instead of the other one. Okay, here you go. Copy this one instead. Like that. V at rest. V at rest. Okay, so here is the vectorial equation: weight, normal, tension, and the force of static friction. The x component of the tension is going to be positive in this case, but the y component of the tension in this specific example is going to be negative. Because the y component of the tension is going to be negative, the final normal force is going to be more than the other two cases, than the other two previous cases. Okay, here you go. Plus, right? Plus. Now, the magnitude of the normal force of this new normal force is going to be more than the magnitudes of the normal of examples 2 and 3. Like that. 2 and 3. I'm going to put here, do an additional step, mathematical step, put the y in evidence. Like that. And everything else that we're doing here applies also to an object moving with constant velocity, okay? And let's do that for constant velocity now. Here you go. Someone else is coming. Yeah. So here you go. I'm at rest. Let's see here. Oh yeah, that's this one here. Here the case, I'm gonna call this one 1A, example 1A. At rest over the surface, V is going to be equal to 0, right? But then I'm going to repeat this problem for the case in which the object is not at rest. Newton, that's the second part of Newton's first law. Okay. An object, here you go. An object of mass m is moving with constant velocity over a frictionless surface. Okay, over a frictionless surface. We have the following force, weight and the normal force. Let's see if I got an illustration for that. We can come up with an illustration for that. And let's not forget this one here. Okay, and I'm going to get the x and y. Not this one. This one has a tension there. That's the one I want. Like that. And now the object is moving to the right. And I can come up with in this case, the net force along the horizontal direction is going to be 0. because the object is moving with constant velocity. Here you go, constant. Constant. For every one of those examples, previous examples that we did, we can have also the case of a object moving with constant velocity. Okay? In this case, it doesn't change much. It's exactly the same thing. In this case, okay, here you go. 2A. There will be one change. Yes, there will be one change. Here you go. And this change, an object of mass m not moving with constant velocity along the horizontal, along an horizontal surface. There is a tension applied to this object to the right. Since the object is moving with constant velocity, comma, there must be another force acting against the station. This force is the force of friction. Specifically, that's where the change comes. The force is the force of kinetic friction. Kinetic, because the object is moving. Okay? It's called kinetic because the object is moving. Consequently, the equation of the net force is going to be net force like that is equal to 0 because the object is moving with constant velocity. Okay. What you see above in reality has, oh, don't forget, that's the change that we have. And I'm going to emphasize here, that's the change is this one. Kinetic. Kinetic. And kinetic. Oops. And here we can do the same. Moving with constant velocity. Not just at rest. An object of mass m moving with constant velocity along the horizontal direction. There's a tension applied to this object to the right. But now we have an angle theta, right? Upwards with respect to the horizontal. Since the object is moving with constant velocity, there must be another force acting against this tension. This force is the force of friction, specifically the force of kinetic friction, or F sub k. It's called kinetic friction because the object is moving. Consequently, the equation, let's see if I have, no. Okay, I'm going to go like that. And I'm gonna emphasize only the K, okay? Like that, like that. Okay, one more, let's see. Here you go, this one. And this one. And we do the same here. or A. Now the tension is downwards, right? The 8 different examples. An object of mass m moving, and I'm going to copy from the other one. Let's see if I can copy everything here. 4B, right? Go. An object of my mass m moving along the horizontal direction. There's a tension applied to the right, making an angle theta downwards. Making an angle theta downwards with respect, making a downward angle theta with respect to the horizontal direction. Since the object is at rest, since the object is moving constant velocity, there must be another force acting against this tension. This force is the force of friction, specifically the force of kinetic friction. It's called kinetic friction, right? Okay, so what changes here is going to be here, promising. And again, I'm going to, don't face it. Don't face it. Okay, here I'm dealing just with the vertical component. It doesn't change at all. Here I'm dealing with the horizontal component. That's what this one changes. And we can find the force of kinetic friction if you know the tension and the angle that the tension is oriented. Okay. 8 different examples. We can come up with other examples. Yeah. Let me erase this thing so I don't have to worry about that. Let's see other examples. Okay, we did that, right? Free body diagram. Well, another example that I want to show you. Here we're having just repetition. I need to, okay, this is one. This is one. Okay, I want something simpler than that. I want something simpler than that, okay? And let's go, now the object is resting over an inclined surface. And this object is not moving. The tendency of this object is to slide down. But because it is at rest, there must be a force of static friction here. Okay? That's the situation that's the physical situation that we have. I can go ahead and put my X and Y axis. Y and X axis, go. Like that. This is the weight. Like that. This angle here is theta. And this one. Equal this one right in here. And I'll put the angle theta. Okay, like that. Okay, that's the situation. And I'll put my right here. I'm going to play the movie again. I like to play the movie, right? So this object, we start with the inclined plane. Okay? Start with the inclined plane. And then we put the object there over the inclined plane. And then I give you the additional information. I tell you the additional information that the object is at rest. Okay. And we go the next step. You know, put the first force that you're gonna put it is the weight. Because the weight is always there. The next force that we're gonna put, oh, now it's going to be the normal. But now it's a different type of normal. It's a normal that makes an angle with the vertical. Because this plane here makes an angle with the horizontal. Okay? And I'm gonna do even better. There's one more thing here that I'm gonna do is to put a flat surface here. I'm gonna put in every one that you have. Okay, here you go. This one, this one, this one, this one. Yeah, this one too. Okay. And because the object is at rest, you must have a frictional force here. Because if you didn't have a frictional force, the object would be sliding downwards this plane. Okay. I don't need this one, but I need this one. Okay. So we have 1, 2, 3 forces in this specific case. Okay, inclined plane. That's the case. The problem with an inclined plane. Example 5A, right? Example 5A. Example 5A. An object of mass m at rest over a horizontal surface. There's no tension in this case. Not over an inclined plane. Inclined plane. There is no tension in this case. Or an inclined plane that making an angle theta with the horizontal. There must, since the object at rest, there must be a force uphill. There's no tension. Uphill, an uphill force. Okay, so I'm gonna do like that. Identify all forces acting on the object. Okay. Okay, so I'm gonna put this way. Here you go. Now, like a real example, right? Since an object at rest, since the object at rest, there must be an uphill force applied to it. This force is the force of static friction. So those forces of friction is the type of force that the ancients didn't understood very well either. Okay. So the ancients didn't understood the second part of Newton's first law of motion, and they didn't quite understand the force of friction either. Okay, this force is the force of static friction that we abbreviate by the letter Fs. In this specific case, we are going to have only three forces, okay? Because I don't have any tension applied to that object. But then you have a situation slightly different, right? Notice that I have oriented my axis anti-parallel to the weight, because I oriented my axis anti-parallel to the weight, right? We are going to end up having a normal that has two components. Take a look here. This normal is going to have a component along the vertical axis and another component along the horizontal axis, right? And this force of friction too. And that's when we come to the realization that we feel. Notice what's happening here. I put my axis along those two directions, right? When I put my axis along those two directions, in the vertical and the horizontal, the weight is written in terms of only one direction. But the normal and the force of static friction, they must be written in terms of two directions. Okay? In this case, we are going to have 1, 2, 3, 4, 5 components of forces to this problem. Okay? Now, watch what's going to happen if I orient my axis in a different, think about that, 5 components, right? I'm going to write that down here. Okay, since the force is at rest, there must be an uphill force applied to it. Okay, here you go. The first force is the weight, right? Is the weight, which is always there, which is always there. The second force is the normal, because the object is in contact with this surface. Since the object is at rest, there must be an uphill force applied to it. This force is the force of static friction. Okay, so we must have 3 forces. So in total, at the total, we must have 3 forces. And the net force is written as, right? Is written as like that. Okay, if I choose an x and y axis along the horizontal and vertical directions, okay, the weight is going to have only one component, right? But the normal and the force of static friction will have 2 components each, for a total of 5 force components in the equation above. Okay? Or I'm going to have something like that. Here you go. net force. Here you go, one component, right? Let's take a look at the drawing here. The x component of the normal force is going to be in the negative direction. So we're going to have something like that. Here you go. I'm going to write like that. N sub x, okay? Right? N sub y. N sub x and N sub y may or may not be positives or negatives, right? May or may not be negative. Make sense? So this N sub x, according to my drawing here, must be negative because the x component is to the left. The y component is upward, so consequently the N sub y is going to be positive. Okay, and then we have to worry about the force of the static friction. The force of the static friction is likewise is going to have x component, right? And I'm going to have a y component because the way we spelled out, the way we chose the x and y axis. Notice that we are going to end, because of that, we end up having 1, 2, 3, 4, 5 components for this equation. Okay? And that's because we choose the x and y axis along the horizontal and vertical directions. However, it is possible to simplify this problem mathematically if we choose a different coordinate system. Okay? A system in which the x-axis is parallel to the inclined surface and the y-axis makes an angle with the vertical. And we usually do that. If we do that, instead of having 5 components, we are going to have only 4 components. If we do that, instead of having 5 components to the forces, we will have only 1, 2, 3, 4, only 4 components. Okay? Let me explain exactly how is that. We have this one, yeah. So here you go. I'm gonna get my x and y axis, and I'm going to rotate like that. Rotate it in such a way, and we can do that, by the way. Oh, yeah. Let's see if I can rotate it a little bit better.
Porque advogando só tem a segunda opção, na primeira não tem esse tipo.
Let's see.
Ó, a primeira classificação de serviço prestado.
Yeah, I think I got it.
Segunda,
I don't know. I keep on showing that thing. Okay, here you go. And by the way, this one is gonna need a flat surface downwards. Right in here. Okay, here you go, x. And now my unit vector x is going to make an angle here. An angle theta with horizontal, right? And unit x, y is going to make an angle theta with the vertical. And I'll call that, pi prime axis to differentiate from the other one. Okay? I'll call that y prime axis. Don't forget this angle. Oops. This angle here that the weight makes is the normal, is the angle theta, right? Under this new coordinate system, we have the following equation for the net force.
É o de baixo, né? Tá bom.
Okay. It's going to have a G along the x-axis, the G along the x-axis. Let me put it in a different way. We're going to have a weight along the x-axis. So let's say that the negative is already implicit there in the relation, okay? And you're going to have a W along the y-axis. The N in this case will have only a y component. And my force of static friction is going to have only an x component. See what happened? What was 5 components along one coordinate axis? It becomes like 4 components along another coordinate axis. Okay, we usually, in physics, we usually use this type of coordinate axis to solve this type of problem, okay? Let's see, 950 right now. I'm not going to elaborate more on that. I'm just giving you some hints how to work with that. And let me erase this part. I'm not going to do any more than that because I want to move forward. Okay. Okay, so let's see. An object with mass m at rest over an inclined plane makes an angle theta, is horizontal. Identify all forces acting on the object. A. Identify all forces that act on the object. Okay. And let's see. Solve this problem using 2 different coordinate systems. One with the y-axis along the vertical direction, and the other with the y-axis making an angle theta, and the other one with the x-axis parallel to the inclined plane. Right? Even better, one with the x-axis along the horizontal direction. Better this way, right? Okay, so here you go. Item A, right? Now, item B. We can organize, starting organizing it. Okay. Which one has the least number of components? Which one has the least number of force components? Right? That's it. The next item, find find the value of the normal and frictional forces. Find the normal and frictional forces, and frictional forces in terms of the non-values. The non-values are what? M, G, theta, right? Those are the non-values. I can see. Let's do that. You go. I can see. We start with this one. We do not need the net force anymore. 955. Okay. So that's gonna be kind of let's see. We're gonna have two equations equal to 0, right? Equal to 0, right? And we can eliminate the vectorial components in the equations. Two equations. One along the x direction, the other along the y direction. And then we can solve for F sub F, for the frictional force in terms of the weight, and for the normal force also in terms of the weight, but it's going to be in terms of the x component of the weight and the y components of the weights. Then you got to do more than that. We got to write that down in terms of mg and theta, right? Going back here, the x component of the weight is this one right in here. Let's go for the next one. Let's see. Yeah, this one. And I'm going to translate. I'm going to ungroup first. Y-axis. I'm going to translate this y-axis right in here. Here you go, right in here. Even better. This angle that you see right in here, okay, this guy is parallel to y, right? This angle that you see right in here is the theta axis, is the theta angle. As you can see, I got something. I got a bug, right? trying to get over the thing. If I was doing this class presidential, I couldn't be doing that, but because we're doing that online, yeah, I can do it. It's less words, right? Okay, so here you go. The projection of the y-axis of this force along the y-axis is going to be this guy here. This angle that you see right in here is the theta angle. But don't forget, the y component of the weight is going to be downwards, right? So here you go. This one here is going to be minus mg. Don't forget you have a minus angle here. And I told you that's going to be cosine, right? Like that. Make sense? I was supposed to do the other one. Yeah, let me translate it here. Okay. And I go the next step. like that. The normal is going to be along the positive direction of the y-axis. Now take a look at the x component of the weight. The x component of the weight is pointing to the left, right? It's this component here. Now it's going to be a sine. A sine because this side is opposite to the angle. And it's going to be kind of similar to what we have here. I'll put it here. The only difference is that the cosine must be replaced by sine. Okay? And I'm going to emphasize that this force of static friction is along the positive direction. Okay? That's what we have for this type of problem. Oh, it's 10 o'clock already. Okay, and then you can do that for the object moving with constant velocity, okay? And there is another relation for this force of static friction, right? That I still didn't introduce to you. I'm going to introduce that to you very soon. So if you repeat that for object moving with constant velocity, right? Moving with constant velocity, F sub S is replaced by F sub K. Okay. And you get something similar here. And I'm going to elaborate more on that about this force of friction, both static and kinetic. Oh boy, it feels so bad. A long time I haven't had something like that before. Gotta go to the doctor soon to get my throat in right place. Okay, let's take attendance. Any questions? See how many examples we did here? We did a total of 9 examples. If you consider the case of constant velocity, for this one would be 10 different examples. And 10:02, let's see. Lab lecture. Today is the 16th. Sky, are you there?
Yes, I'm here.
Thank you. Tessa?
I'm here.
Thank you. Destiny?
I'm here.
Thank you. Gaia? Gael Garcia disappeared, huh? Let's see what he did. He was there, but he didn't. Okay, read one here. Let's get there. Okay, thank you, read one. I'll get to you, Camden. And Ashley, are you there? Thank you. Norberto? Annabelle?
I'm here.
Thank you. Vanessa?
I'm here.
Next is Catherine. I don't see Catherine here. Camden, now it's your turn, Camden. Okay. Oh, I'll give attendance. Victoria Preciado.
I'm here.
Thank you. Alexis.
I'm here.
Okay, and Marco Sanchez. Okay, let's see how many students we have it. 12. Yeah, we have 12. Good, and let's go for our break. Break. from 10:05 a.m. to 10:20 a.m. Okay. So I'll see you in 15 minutes. See you. Okay, I'm back here. So yeah, consider that we are done this part of first law of Newton. And this one here I want to pick up. And now let's go for the second Newton's law. Okay, so okay, go here. Here's an illustration of the weight, okay? What you have to know about the weight is that this force is a force that comes along whenever it's nearby a very large mass, like the Earth is nearby us, okay? The Earth is attracting everybody towards the center, and we are all subjected to the weight. Whether you're on the surface of the Earth, in the surface of the moon, we have a weight. We are subject to this force called the weight. And then, keep in mind that weight is not the same as the mass of an object. Okay? Weight is a force, whereas the mass of an object is a basic quantity, right? Weight is not the same, it's not the same as a mass, but they are related to each other. Okay? Weight is m times g. So now let's talk about second Newton's law. And very soon I'm gonna tell you more about the force of friction, okay? But before that, let's talk about Newton's second law. Okay. According to this law, we have the following relation. Net force is equal to mass times acceleration. That's what you have to remember. Okay? Can you remember that? What you have here is actually three equations, three scalar equations. Let me see here. Can get, okay, let's see if we can do that. Here we go. Yeah, this one here. Yeah, good. Okay. It's gonna be, the net force along the x direction, right? Is gonna be equal to mass times acceleration along the x direction. The net force, I'm gonna put an arrow here instead. Here you go. Along the y direction is going to be mass times acceleration along the y direction. Okay, so that's what you have to remember. This is a law of nature. It cannot be derived. That's why we cover acceleration, right? Because the force is related to the acceleration, that is also related to the mass. For this specific case here that you see here, an object, under free fall is subjected only to one force, the weight. Okay? Example. Here you go. An object under free fall is subjected only to its weight. Find its acceleration. Okay? That's going to be a very simple problem. Okay, so here you go. Because the object is under free fall, the net force applied to this object is just the weight. Like that. And let's not forget that the weight is given by mg y hat, right? With a negative sign here. Do you see that? And then the m cancels out with this m. And what we get? We get this result here. The acceleration is just like you already knew, right? You already knew that. An object under free fall is subjected to the acceleration of gravity. And then there are other types of problems that we can come up with. Let's see, I have, I want to, yeah, okay, I'll have to, okay, I have to make up one example here for you. Yeah, let's go ahead and use this one, this illustration. A mass resting over a frictionless surface. Okay. Okay, so here goes. Example, another example. I call that example 2, right? Example 1, example 2. A mass, an object of mass m is resting over a frictionless surface. Let's put some numbers now, right? 1 kilogram. A force a horizontal frictionless surface. A force of 1 Newton is applied to this mass along the horizontal direction. Find the mass acceleration. Okay. So we have this net force. Let's see, yeah, I'll call that force of one is applied to this mass along the horizontal direction. Okay, and this force, instead of T for tension here, I'll put force F. Okay. Frictionless surface, there is no friction, right? And because there is no friction, we must end up, the mass must end up with an acceleration. That's how you represent an acceleration to the right. I'm going to put the mass M here. The object has no acceleration along the y direction. Has acceleration only along this horizontal direction. Okay. So here we go. Net force is going to be W plus N, right? Plus this force F. That's how we set up our problem in a vectorial fashion. No acceleration along the y direction means that we have only acceleration along the x direction. Like, oh, no, it's not what I want. I want a hat. There you go. Because
Professor,
those, yes.
what is N stands for?
Which one?
N?
This one here
Yes.
means the normal.
No.
Yeah,
Okay,
the normal. This force here, normal. Okay, and here's the weight. No acceleration along the y direction means that W plus N is equal to 0. Right? And we are left just with this force along the horizontal direction. Okay, and I want to find out this guy here. Plugging in the numbers, we have 1 Newton, 1 kilogram, and now I'm doing everything in a scalar fashion, right? We end up with an acceleration equal to, 1 Newton over kilogram, like that. But according to Newton's second law, right? According to Newton's second law, F equal to ma, right? I'm going to take out the vectorial symbol, make it easier for us to see what I want to express here. We have that the unit of mass of a force must be equal to the unit of mass times acceleration. which is equal to the unit of mass times the unit of acceleration, right? Why am I doing that? Because there is a relationship between Newton, kilogram, and second. Okay. Here you go. Continuing this equation right in here. The unit of mass is kilogram. The unit of acceleration is meter per second squared. Okay. And let's not forget that the unit of force is the Newton. So we end up with this dimensional relation. Okay. Replacing, substituting that right in here, right? We find what we are supposed to find. We find that the acceleration, the unit of acceleration is going to be the meter per second square, okay? So it makes sense, right? This result here. So what acceleration we end up getting is 1 meter per second square. That is the simplest problem for Newton's second law you will see out there. Well, actually, it's the second simplest problem, not the first simplest problem. It's the second simplest problem. The first simplest problem is this one right in here. This is the simplest, this one here, the first example, simplest problem you will see. In Newton's, for Newton's second law, okay? That's the simplest problem. The next in simplicity is this one here. Okay. So here's the free body diagram. Don't forget to put the acceleration there, right? And now okay, so let's see here. Yeah, we're going to, oh yeah, and then I'm going to, okay, now I'm going to talk about the force of friction that I didn't talk about yet. This thing here is going to come later on, okay? Those illustrations that you see here is going to come later on. Let us talk about the force of friction. And let's see if I have a graph here that I need to show you. Yeah, too bad. I don't have a graph here. Gotta do that from scratch. Okay, for some reason, the graph that I want is not here. Okay. Let me copy this one. Put it here, and I'm going to erase this guy that I don't need it. Okay, so let's go back to the force of friction. You already know that there are two types of force of friction. Static and kinetic. Kinetic or dynamic, we also give it the name Okay. Represented by F static and F kinetic. Oh, see, like that. I'm going to elaborate that. There is more things that you have to know about the force of friction. Let us start with the force of static friction. Okay. The force of static friction has this strange behavior. So, and I'm going to emphasize it right in here. When I get this object, put over a surface. And I'm going to apply a force to this object. I'm going to perform an experiment, okay? And you can do this experiment at home too, it's not difficult. Let's see if I can do that here. Yeah, not this side, this other one. Yeah, let's see if I can do that. Yeah, I think this one is better. Okay, good. Let me stop sharing. Remind me to share again, okay? So here you go. Here we have this surface here, which is in contact with this other surface, my checkbook and my cell phone, okay? Have you ever noticed that once you apply a force to an object, the object doesn't move necessarily? Have you ever noticed that? Right? Try to make your chair move, or your table, or your bed, okay? You cannot get it moving even though you're applying a force, because there is a force of friction. And this force of friction is the force of static friction. Okay, I'm applying a force. At this moment, I'm not applying any force to this object whatsoever. I'm applying zero force. So if I start with a force equal to zero, the object doesn't go anywhere. Here you go. Here's zero, representing zero force. Okay, the object doesn't go anywhere. It's at rest. Go V equal to zero, right? Consequently, the force of static friction in this case is zero. But if I increase this force, let's say to 1 Newton, and the object still does not move, that's because we have a force of static friction being applied on this object in the other direction. No, not this one. This one here. Here you go. Now you got it. Make sense? And I'm going to put it a red color. So we usually represent the force of friction right there at the interface. Here's the force F. Oops. Oh, what's going on here? And here is the force of static friction. Here you go. Okay. So likewise, if we increase this force, let's say to 2 newtons, this force of static friction is also going to increase, but the object is going to be still at rest. That's what we observe. Okay, and again, let me copy and paste, make sure everything is
Can you share your screen again?
Oh, thank you.
Thank you.
Thank you, thank you, thank you, thank you. Okay. Okay, so here you go. Now, if I increase this force to 2 newtons, for instance, and the object still does not move, so we can say that the force of static friction is going to be 2 newtons as well. However, there will be a point in which the force is increased to a point where the object is about to move. It's in the verge of motion, okay? That's what we do observe in real life. And at this point, the force of static friction becomes the maximum value of the force of static friction, okay? That's what you have to know about the force of static friction. The force of static friction is a little bit more complicated than force of kinetic friction, okay? So if you understand how the force of static friction works, then you understand how the force of kinetic friction works, okay? So let's write it down, but I just told you. Static friction, okay? If you have an object resting over a surface, if you have an object at rest over a surface, and no force is applied to this, I have an object at rest over a horizontal surface. I have to specify that horizontal first, and no force is applied to this object along the horizontal direction, comma, we say that the force of friction applied to this object is the force of static friction. No? If you have an object at rest over horizontal first, if you have an object at rest over horizontal surface, let's see, I'm going to put that later on. We say that the force of friction applied to this object is a force of static friction. Okay? If no force is applied to this object, then the force of static friction is 0. However, if you start applying a force in the horizontal direction to this object, and it still doesn't move, it still does not move, we say that the force of friction is no longer 0, but has a magnitude equal to the magnitude of the applied force. Of applied force. So let's say, example, right? You apply 1 Newton of force in the horizontal direction to this object. If the object does not, if the object still remains at rest, you know from Newton's first law that the force of static friction is also 1 Newton, right? Consequently, if you apply 2 newtons and the object is still remains at rest, the force of static friction is 2 newtons, and so on. However, there is a limit to how high, right? The force of static friction can go. There's a limit to that. Okay. At this point, the object will be at the verge of motion. Okay. Okay. This force of static friction, where the object is at the verge of motion, is the maximum value of the force of static friction. Okay. In this case, we say that, and then there is a relationship for that. An important relationship that I want you to memorize. You go, the maximum value, we go of the force of the static friction is going to be given by a coefficient that we call it mu sub s, coefficient of static friction, times the normal. Okay? Do you see this relationship here? The force of the static friction depends not only of this coefficient, which is a new type of coefficient that you're seeing for the first time, but it also depends on this force, the normal force. You see how important the normal force is? The higher the normal force, the higher this maximum value of the force of the static friction. Okay? So we can here write this equation the following way. Okay, so here you go. The force of static friction can have a value anywhere between 0 and this maximum value. Even better, I'm gonna invert that from the left to the right, right? Let's invert that. I'm gonna do like that. Here you go. Like that. It's better. And then I'll copy and paste it here. Yeah. This one here. Do you see how it goes? In another way, I can here write it in another way. And I'm gonna tell you more about this coefficient of static friction. Okay, I'll tell you more about this coefficient of static friction. Graphically speaking, that's what we usually do. And in a graphical sense, we have the following. If I plot the force O, the force of friction along the y-axis, not the force of static friction, but the force of friction in general along the y-axis, and the applied force along the x-axis. Don't forget this force must be along the horizontal direction. We have the following relationship. We have a linear relationship between those two. Okay? We have something like that. This slope here is 45 degrees. the force of friction is directly proportional to the applied force. And then there is a limiting, right? There's a limiting value for this force of static friction. Like that, you go. Okay. And this limiting value is given by the maximum value of static friction. This point here, when we reach the maximum value, and I'm going to like that. Like that. At this point, if you exceed the applied force, something interesting happens. Okay, if we exceed this maximum value, the force of friction decreases momentarily. The object starts to move, and what becomes of this force of friction is no longer. I'm gonna go a little bit more lower here, so you have enough space. Yeah, let's go like this lower. There's a discontinuity, okay? And the force of that was initially a force of static friction, so it becomes what we call the force of kinetic friction, and it's not a maximum value. The force of kinetic friction doesn't change in value, okay? What changes in value is the force of kinetic or static friction. From here to here, see here, in this region, the object is at rest. Okay. And I'm going to, let's leave this way. The object here is at rest. V equal to 0. And in the other region, the object is accelerated, is moving. Not necessarily accelerated, but moving. All depends on the applied force, right? Let's see, different of 0. I'm gonna put the magnitude of V. Magnitude of V greater than 0. Like in this region here. Okay, and don't forget that's the applied force here. It can be accelerated. Especially speaking, in this case here, it will be accelerated. You know, even better. I wanted to put V different of 0, but that's it. That would be better if you put V different of 0. And the acceleration would be greater than 0 as well. That's how it works, okay? Once the object starts moving, the force of friction, the force of static friction becomes the force of kinetic friction. And the force of kinetic friction, by the way, is given by a similar formula where it's going to be force of kinetic friction, coefficient of kinetic friction times the normal. In general, okay, this coefficient here, in general, is going to be greater or equal than this other coefficient. We have the above coefficients, depend on the nature of the two surfaces that are in contact with each other. Okay. The values, right? The values of the above coefficients depend on the nature of the two surfaces that are in contact with each other. Let's take a look there at the book. I want to go to, every book has a nice table showing the values of the coefficient of kinetic and static friction. You can look that you can also look at that in Wikipedia, okay? Okay, let's take a look at Wiley course resources. Lunch. Newton's second law of motion, blah, 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 vector nature. We're going to get to that. We didn't cover Newton's third law yet. Gravitational force. Let's see here. Normal force. Oh, here you go, right in here. Okay. See, we have two surfaces. The surfaces are not completely flat. They have some microscopic, microscopically speaking, they have those ridges, right? And that's what causes the friction, because the surfaces are not completely polished, not completely flat. Okay, and let's take a look here. Static frictional force. Don't forget that the maximum value of the static friction is equal to that. Here you go. Here's a table of the coefficient of static friction. If you put two pieces of glass that are dry, okay? If you put water, the friction is going to be different. The coefficient of the static friction is going to be 0.94, and the coefficient of kinetic friction is going to be 0.4. Remember, I told you static friction is greater or equal than kinetic friction. Ice on ice, very little friction. Okay, whenever it's moving. Rubber on dry concrete, just like the case of your car. The rubber of your car in contact with concrete, dry concrete, right? That's the coefficient of static friction between the rubber and the concrete. If the tire of your car is not at rest with respect to the concrete, the coefficient of friction is less, it's 20% less. If the concrete is wet, the coefficient of static friction decreases by 30%, and so on, okay? Those are different values that we can measure in the laboratory. Note see the Teflon. Teflon is that plastic film that's in your frying pan, okay? Teflon has this interesting property. It has very little friction. Look at the value compared to every other, and the coefficient of kinetic friction is equal to the coefficient of static friction for two surfaces of Teflon. Very little friction. Okay? Wood on wood, etc. Let's copy and paste that in the book, in the notes, is nipping tool. But you can also look at the,
Professor,
yeah,
I have a question.
yes.
So, let's say if you applied like 3 newtons of force, right? And then
Uh-huh.
the object is not moving. That means like either the friction is like greater than or equal to 3 newtons of forces.
It means that the maximum value of the force of friction is greater or equal than 3 newtons. That's what it means, the maximum value.
Oh,
Okay?
maximum value.
The
Okay.
maximum, yeah, the maximum value.
So
Okay.
once the the object is moving, the friction worked as a mass or the
Well, let me illustrate that here, right? Like I illustrated before. Here you go. So I'm gonna copy and paste it here, right? We started that force equal to 0, right? Force equal to 0. The force of static friction is going to be, force of static friction, right? Is going to be 0 as well. Let's see here, subscript, okay. Okay, it's gonna be 0 as well. Force of static friction, not the maximum value, right? We can, I'm gonna put that in red. Now, if I increase my force, my applied force to 1 Newton, right? And then I'm going to denote that by increasing the arrow. And the object is still at rest. The force of static friction is still 1 Newton. Is also 1 Newton. You increase your applied force to 2 Newtons, and the object is still at rest. The force of static friction is also 2 Newtons. Right? And then let's say you reach a point in which the force of static, the applied force is 3 Newtons now. Okay? The object is still at rest, but it is on the verge of motion, right? How I'm going to represent that? I represent that by the fact that, that's how we usually represent, when the object is on the verge of motion, right? We have those little dashes, right? Here you go. Object on the verge of motion. Let's see, group. When I group that, here you go. Verge of motion. And I even going to emphasize here, object on the verge of motion. Like that. A little bit larger, right? Object on the verge of motion. This force of static friction. Now we say, oh, what happened here? Interesting. Shouldn't be doing that. Let's try again. Okay. the force of static friction in this case is going to be the maximum value of the force of static friction. And anything that you do, a little disturbance, will make the object move. Okay? And there is a relation here, right? And the relation is what? The relation is mu. Oh, not that. Mu. Font symbol. Mu times n. It's not mu max times n. It's just mu s times n. Okay. An example. Okay? I'll put it down here. So see, the object is on the verge of motion. That's why it has those.
What's the next step of the object on the verge of motion? Well, then
Yeah. Okay. If you increase now the next step, what would be the next step? Suppose now that you increase the
Newtons.
force. Let's say to 3.1 newtons, right?
Okay.
Okay. Suppose now the object is no longer at rest. Okay. The object is no longer at rest. It starts moving. Okay. The force of friction is no longer the force of static friction. It becomes the force of kinetic friction, which is less than the maximum value of the force of static friction. Okay. Which, by the way, is less, yeah. Which, by the way, I'm not gonna put, here you go. Which is less than 3.1 newtons and also less than value of
So
okay.
force of friction is always greater than force of kinetic, right? No
Force of
exception.
static, force of,
I mean
not,
static.
wait a minute. The maximum value of the force of static friction is always greater than the force of kinetic friction. That's the right way of spelling that out. Okay?
Can you write it down for
Yeah,
us?
I will write that down. Here you go. Let's see. The maximum value of the force of static friction, you know, don't forget, it's let's see, what am I doing here? What do I have F sub? Oh, that's F sub S. Okay, here you go. The maximum value of the force of static friction is greater or equal than the force of kinetic friction. In general, it's greater. Okay, in general. But there are cases in which they are equal. Okay, so in other words, it's going to be like that. Okay. Remember, it's always less or equal than the maximum value of static friction. It's not necessarily less or equal. This one doesn't apply. Okay. This one here doesn't apply. The force of static friction may be less than the force of kinetic friction, but not the maximum value. So how do I do that? Don't mix up this thing with this thing, okay? Let's see how I put a dash in there. I'm going to spell that out here. The force of kinetic friction is not necessarily less than the force of static friction. It may even be more. Okay, what we are talking about here, and that's what many people don't understand, right, is the maximum value of the force of static friction. Okay. Remember, the force of static friction can be anywhere between 0 and this value, right? That's why I'm saying the force of static friction by itself may be less than the force of kinetic friction, maybe less. What I can tell you for sure is this relationship here. This relationship always holds. Okay? This relationship here always holds. The coefficient of static friction is always greater or equal than the coefficient of kinetic friction. Okay. So, and just, if you can also go back here, right? See, you have those values of force of static friction, right? In this region here, where the object is at rest, the force of kinetic friction is obviously greater than the force of static friction. But in this region here, the force of static friction is greater than the force of kinetic friction. And the maximum value of the force of static friction will always be greater or equal than the force of kinetic friction. That's another way of seeing this relation. Let's take
I
a
have a
break.
question.
Yeah, go ahead.
One more question. But how do you know when it reaches to object on the verge of motion? Like, how can you tell if it's like a maximum level? Like,
I will tell you in the problem. If
okay.
if I give you a problem, I'm going to tell you the object is on the verge of motion. Okay.
Okay.
The object is on the verge of motion. Then I'll tell you that.
Thank you,
Okay.
Professor.
But I can also ask you, look, the coefficient of static friction is this value here. The object is resting over a flat surface. And then I ask you, what is the maximum value of the force of the static friction? I can ask you that as well. What's the maximum value, right? What is the applied force? What's the force that I have to apply to the object so it is on the verge of motion, right? I can ask you this question, right? Question that can be asked, right? Let's
Yes.
see. Yeah, let me write that down. Examples, right? Given if the coefficient, an object, there you go, an object of mass m is at rest over a flat surface, horizontal flat surface, right? Okay, so what is the maximum value of the force of static friction, right? I can ask you that. Oh, an object of mass m is at rest over a flat surface. It's a coefficient. Its coefficient. You need one more information here. Its coefficient of static friction is mu sub s, right? Mu sub s. Symbol. Right? What's the maximum value for static friction? And then I can ask you another question. What is the value of the applied force, right, for the object to be in the verge of motion, right? Okay, those are possible problems that you can have. Okay? One more question. Okay, 11:19. Let's see, very soon it's gonna be 11:20. Let's put a break, 11:20 a.m. to 11:35 a.m. Okay, I'll give you some examples, better examples. Okay, we're gonna do some examples when we return. And then we can go for the third law of physics, okay? So far, two laws of physics, right? First and second law. 11:20 right now, and then I'll see you in 15 minutes. Stop sharing. Back here. Okay. Okay, so let's take a look. Okay, let's come on. Example. Okay, so I'm gonna make like two different examples here. Example. First, flat surface. First, we're going to do a flat surface. Flat surface. Okay. Calculate the maximum value of static friction for the case in which, the coefficient of static friction is 0.5 and the mass is 100 kilograms. For the case in which, and the mass is at rest. The mass is at rest. Okay. Okay, so calculate the maximum value of static friction. Okay. For the maximum value, for the case of a flat surface, we already know that the normal is equal to the weight of the object, right? It's equal to the weight of the object, which by the way is mg. Mg. Okay. Mu sub s is half. M is 100 kilograms, right? And G is 10 meters per second square. G, okay, here you go. Here's half. I gotta put half, right? So what we end up getting, it is what? 500. 500 newtons. Okay. Now let's compare with this other one. Another example. The only difference here is that the object, is plane, inclined surface. Inclined surface. 30 degrees inclination. Going back, we always need to get our drawings here in place. Otherwise, we might not be able to get our result, okay? So here you go. I will put it right here. That's the situation. This angle here is 30 degrees. And we calculated before that the normal is going to be given by mg cosine of theta. Do you remember that? We did that before, right? If we go back to our previous case, let's see here. Normal, yeah, the y component of the weight, mg cosine theta, see that? So we can go ahead and copy that. For this case is different from the other one, right? This equation that you see, let me put that here. This equation that you see here is the same as this equation. But what is different? What is different is the normal. The normal here is different from the normal here, right? The normal here is going to be mg cosine of theta, because that surface is inclined. Okay, substituting that, we have something like that. Mu sub s is 0.5. 0.5, okay. I'm gonna copy all of that, right? The only thing that's different is this one here, 30 degrees. This one is going to be 500, right? This one here is going to be 500 newtons. But the cosine of 30 degrees is going to be what? Square root. Okay. Square root of 3, right? Over 2. Oops. Like that. Square root of 3 over 2 is going to be less than 500 newtons. Okay, this one is going to be less than 500 newtons. You can calculate it. Square root of 3 is 1.7, right? Divided by 2 is 0.7. So it's going to be around 350 newtons. It's going to be approximately 300. We can do that with the calculator. Let's see here. Divided by 2 times 500. Oh, this more. Is 433. Okay, square root of 3. Oops. Yeah, divide by 2 times 500. Yeah, 433. Which is less than. So whether the surface is inclined or not, it it affects the value of the maximum value of static friction. Okay. I'm going to copy and paste the coefficient of static friction for some surface, some pairs of surface, okay? Steel on steel is 0.74, rubber on concrete is 1.0, 0.8, rubber on asphalt is slightly less, just slightly less. You can look out there the exact number. So it's, in a way, it's safer to drive on a concrete surface than to drive on asphalt surface. It's slightly safer. Aluminum on steel, glass on glass, Teflon, Teflon, right? Ice on ice. And the synovial joints in humans, look at the low value of the coefficient of friction. Very small, right? And I want you to do some problems on that. And what I want to do now is third Newton's law. Newton's third law of motion. There's many examples that you can get for forces and acceleration. What's Newton's third law? Okay, Newton's third law of motion is the following. If two objects, I'm going to, if two objects are interacting with one another, and by interaction I mean one object apply a force to the other one, they apply a force to each other. They apply a force on each other, right? That's what I mean by interaction. Interaction means a force. Then the force that object one exerts on two is equal in magnitude and opposite in direction. This is a very important law, folks. Here is the notation. Force of one in two is equal to the force of two in one. But because this is a vectorial quantity, we must have this negative sign. Force of one in two means force of that object one applies to object two. And so on. Fij means the force that object I applies on object J. Let's take a look at what exactly it means, okay? We have some illustrations here. Oh, here you go. It's the case of my mass hanging there no, in free fall. What does it exactly mean? It means that the Earth is pulling the object towards its center. If I call the Earth the object number one, okay, and the mass the object number two, let's put it here. Let's put it outside. Here is the force that the Earth exerts on the object. Force that object one exerts on two is towards the center of the Earth. But the object number two also exerts on a force on Earth, which, by the way, is equal in magnitude, but opposite in direction. That's how I represent it here. Even though we are being attracted by Earth, we are all attracting the Earth towards us. Every human being is doing that. Okay. That's how we do that with free body diagrams, right? In free body diagrams, if I want to know all the forces in one of the objects, we draw a square around the object of interest and we dash the other object. That's what I did here. And similarly, if I want to know the force on Earth alone, I would dash this object, right? And would draw a box on this. Why is it not doing that? Huh. Interesting. Huh. So odd. This box is not okay. Now he did it. Good. So let's see if I can. I'm going to, instead of dashing it. Okay. Now this one becomes like a solid, and this one here becomes dashed. That's how we illustrate right here. We do the same thing. We're just emphasizing the fact that we are paying attention to Earth itself only. Okay, like that. Now, the net force in this object is going to be F of 2 in 1. The net force in this object is going to be F of 1 in 2. But then there's another way of looking at this problem. What if I come to you and say, look, my system is both the Earth and the mass itself. There will be instances in which you're going to have something like that. Okay, and now in both cases, all the forces are no longer being dashed, and the object is going to be solid. In this case, the net force is going to be 0. Okay, in this case, the net force is going to be 0. Oh, here you go. The case of two magnets, another example. Magnet 1 and magnet 2. Okay, they can either repel each other or attract each other. Okay, repel or attract, and then you can go through the same exercise that we did before. We can isolate this object here. This one's going to be dashed, and the only force that is going to be of your interest is going to be this force to the left. And similarly here, okay? They are interacting. Those two objects are interacting. You have to do this. This is steady. The case of my hand up, in contact with the wall, right? If I'm looking just at the forces applied to my hand, so what happened? The wall is going to be dashed. This force, which is the wall, right? Object number 2. This force is going to be dashed as well. And we'll be looking just at this force here. F of 1 in 2 is equal in magnitude and opposite in direction with respect to F of 2 in 1. Okay, those are examples of the third law. We have this example too, and let me, before I give you the answer, right? Consider the case. Consider the case of a string attached to a mass, an object like that. The string is object 1. The mass is object number 2. Let's here you go. I'm gonna do step by step here, right? Okay, the surface of the object. We put object 2 here. I'll call that object 2. And then 1154, right? And then we attach a string to this object right in here. A string to this object. The string is going to be object number 1. Okay. I don't need that. Right? Surface, mass, string. Okay, and what's gonna happen? The string will apply a force to the object 2, force of 1 applied to 2, and according to Newton's third law of motion, okay, and force of 1 applied to 2, the object will apply a force on the string in the other direction. Okay, and then I can, illustrate the pairs of forces like that. I'm gonna displace it just a little bit here so you can still see the string, right? Okay, force of 1 in 2, force of 2 in 1. go, Earth and Moon. Earth and Moon, another example. The Earth is attracting the Moon. Force of 1 in 2. The Moon is attracting the Earth. Force of 2 in 1. The force, those two forces are the same. And now we can have 4 more minutes, right? We have this problem here. Okay, this is a very interesting problem. Oh, I need to turn on my video. Okay, were you seeing the screen, by the way, all this time? I just noticed that I didn't turn on my video. Did you see the screen all this time, or yes or no? Okay, but
The
what about
lecture, yeah. Lecture,
Okay,
yeah,
okay.
but not your face.
Okay, yeah, it's just my face that you weren't able to see, right? Okay, good.
Exactly.
Yeah, okay. So the screen you were able to see it, right? I was sharing the screen with you, but not my face, man. Okay, good. Good to know. Let's see, 1157. Okay, think about this problem here. This is a very interesting problem, which uses Newton's third law of motion. You have, I won't have time to solve it now, but at least I'm going to set that up for you. We have a force being applied to those two objects that are attached to each other. One is touching the other. Okay. The first thing that you're going to ask you, what's the acceleration of the set of those two objects? Okay. So what do? I select mass 1 and 2 as my system. Okay. As my system. And then, I can find the acceleration using Newton's second law. Okay, that's how you treat it. Mass 1 and 2, treat them as a single object because it's our system. The acceleration is going to be given by the force divided by m1 plus m2. Okay, but then there is this other part of this problem. What's going to be the contact force between m1 and m2? Okay, what's going to be the contact force between m1 and m2? What's the contact force? Yeah, what's the force that 1 applies to 2, right? So you isolate mass 2. Mass 1 becomes like this ghost, this little ghost that you see here. And what are the forces applied to the mass 2? It's going to be the weight, the normal, and this other force, F of 1 applied to 2. F of 1 applied to 2 is not necessarily equal to this force here, folks. It's not necessarily equal to this force. Okay? Those two forces, N2 and weight, they're going to cancel out. So everything that's left, F12, and F12 is going to be equal to mass 2 times acceleration, okay? And then you can do the same for the mass number 1. And I'm going to do that in detail next time. Okay, any questions about that?
But why is the small box force 21 is going opposite direction when you compare to the big
because
bigger.
of Newton's third law of motion, right? Those two objects here, those two objects are interacting with one another, right?
Mhm.
Okay, this object is applying a force to the right on object number 2. Due to Newton's third law of motion, this object will have to apply a force to the left. That's why it's gonna, that's why in this case F12 is to the right, and in this case F21 is to the left. Okay, because the reaction, we call it the reaction force.
Reaction force.
Yeah. Okay, even better. I'm simplifying it here, and I can also let me illustrate it in a different way here as a whole. I'm going to illustrate it as a whole in the last slide right here. Okay, so here you go. This one I'm going to dash out. Hey, I don't like that. Maybe this one? Yeah, no. This one is better? Yeah, this one is better, right? Okay, those are action-reaction pairs. We call it action-reaction pairs. The magnitude is the same, but the direction is opposite. And this one is an external force. Okay, so 12:01 right now. And that's what we have. I'm going to stay here for the office hours. And if you want to ask any questions, I'll be here for the next hour. So see you Wednesday. Yeah.
So I have a question about the previous lecture videos.